In this video, I want to just take a minute to talk through an overview of our chapter on gas laws. Um, so I'm going to try to distill it down into a little bit of a nutshell. Hopefully that'll give you an idea of what to focus on. So as we start discussing gases, we are going to really be looking at the behavior of gas particles. And this will lead into our understanding of how molecules actually interact with each other when they're closer. When they're far apart from one another in a gas, they don't really interact very much. And so we can see that a gas will behave in the same way no matter what its chemical identity is. And that's a super cool thing. It gives us a lot of predictive power. So I think that this chapter can really be characterized into kind of two main areas. First of all, our gas laws, and secondly, kinetic molecular theory. Which is really our theory about how these gas particles are behaving. And this is kind of a chicken and the egg thing. Like it's really helpful if you know both at the same time. We introduce it through the gas laws, and then we look at kinetic molecular theory specifically and look at a few things off of that. But it's always kind of helpful to understand the gas laws through the lens of how these molecules are behaving. So within our gas law piece, let's start there. We're going to introduce you to a handful of equations. And there's a whole bunch of them that are going to be named after like dead scientists. And so we have all of these small individual gas laws. I'm just going to call them simple gas laws for now. And these are like Charles' law, Boyle's law, blah, 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 blah. So a whole bunch of these things. Well, we can combine all of these into one simple, simple might be the wrong word, one kind of summary equation. And what all these gas laws are doing is they are describing relationships between variables. And so when we look at a gas and at a gas behavior, we can see things about its temperature, the number of particles that we have. So that's like the number of moles. So that's going to be N, temperature's T, the volume that gas occupies, and then also pressure. And pressure might be the one variable here that we haven't actually really talked about before, and it really just applies to gases. Pressure is really just the force with which a particle hits a surface. So it's that force over area. That's so my hand right now, the atmospheric gas around me they're all these particles are constantly hitting my hand, and that is generating the pressure against my skin of just the air around us, the nitrogen and the oxygen and the carbon dioxide around me right now. So we're going to be looking at these variables, and these lead to the ideal gas law. And this is just literally combining a whole bunch of smaller individual relationships into one big thing. This is we call it Pluvnert. We sound it out, but it's pressure times volume equals the number of moles times R divided by T. And that R is not one of our variables. That R is actually a constant. This is our universal gas constant. That numeric value depends on the units you're using. You want to match the units of your ideal gas or your universal gas constant with the units that you have for pressure and volume. And we always use the same one for temperature. So we want to make sure this matches our pressure and volume units. Our units we'll always use for temperature will be the same. These will always be in Kelvin. N is moles, it's always going to be moles. Pressure, a lot of times we'll use atmosphere or millimeters of mercury. And for volume, we will use liters almost exclusively. So that's our ideal gas law. And you can use that if you know about the pressure and volume and the number of moles, you can figure out what temperature that gas is at. And so it's kind of like if I have 3, I can find the 4th. We have another gas law that we also use other than the ideal gas law, and that is the combined gas law. And this is useful when we're looking at a comparative situation. So when we are looking at the pressure before and after some sort of change, or the volume or the temperature before and after. And this is, again, just a combination of these simple gas laws, but it's the pressure times the volume divided by temperature in situation one. Then a change occurs, and it'll be equal to the pressure times the volume divided by the temperature. Basically, this says if I change one of these variables, like if I change the temperature of a gas, I will see a change in its pressure and volume. All right. The other one that is super important is Dalton's law of partial pressures. And this just states that the total pressure for a mixture of gases is the sum of the pressures of each of its components. So like P total equals P1 plus P2, which sounds super straightforward, but it's easy to forget about it. What we use this a lot for is when we are doing experiments and water is present. This allows us to account for any other gases in our system that aren't part of the reaction we're doing. And that's usually water. So we'll see a lot of vapor pressure of water problems for this. A lot of times, if you want to collect the gas to study that's generated in a reaction, you would collect it over water. So that way it's in a spot rather than in a balloon. And so in that space where you're collecting this gas that you formed, you also have some water present, because any body of liquid water, some of the particles will have enough kinetic energy to actually exist in the vapor state above the surface of the water. So any liquid water has a little bit of gas water above it. And so we just need to account for that gas water above it. All right, so these are the main gas laws that we're going to use during the quarter. And there's a variation on the ideal gas law, a variation that is the real gas law. And this really comes to us from kinetic molecular theory when we get into this. So the real gas law is going to provide a way of compensating for some of the assumptions we make in our ideal gas law at extreme temperatures and pressures. The ideal gas law works great for predicting gas behavior at like atmospheric room temperature, right? Or sorry, at sea level and at room temperature. But the second we kind of get outside of that best case scenario, real gases will behave slightly differently. And it's based on the assumptions that we make with kinetic molecular theory. So in kinetic molecular theory, we are assuming a number of things. One, we assume that these particles are extremely small and that their volume is negligible. We also assume that these particles, like gas particles, won't interact with each other because they're so far apart. We also assume that they will always be moving in random straight lines. So it's like constant, random, straight motion. That the particle will keep moving until it collides with a wall, and that's really what generates pressure. And lastly, that the average kinetic energy of the gas will be proportional to the temperature. All right, so these assumptions allow us to like make predictions, but the real gas law corrects for a couple of them. That is that the volume of these gas particles is negligible and that they don't interact. They do interact if you get them close enough. It's just they're usually really far apart. And these do have volume, even though they're very tiny. But if you can imagine a gas that then is compressed to a very small volume or it's under very high pressure, then those gas particles are going to be much closer to each other and they can actually interact. They're also going to take up a meaningful amount of volume in that container. And so we use the real gas law to correct for these assumptions. And we only need to use this equation when it's appropriate. Like we don't need to do it when we're looking at a gas at, 1 atmosphere of pressure and at 298 degrees Kelvin. But it's a correction to the pressure, which is, I'm going to give it to you here, and a correction to the volume. And so A and B are constants that are going to be unique to each molecule. Oops. And so you would need to look those up, and then you can actually calculate, oh, I'm going to have this pressure instead of that pressure. And the pressures that we're seeing here, these are the ones, so like here. So this piece right here, all together would be our real pressure. And this whole component right here, volume minus N times B, would be our real volume. Whereas that pressure and volume would be our assumed, like our actual, like the given amount, right? Like I expect this volume. All right, so that's the real gas law, and it's not really tricky about when to use this equation. It's just tricky solving this equation and plugging it into your calculator. So that's where the real problem arises with that. So that is the real gas law. A few other things that we can do with the ideal gas law or with the other different, like the combined gas law and things like that, include calculating molar density. And in this, what we're doing is we're really using the fact that we have like we have moles per liters, like we can set up N over V, right? And we can equate N equal, so would be equal to pressure over RT. And we can also use our molar mass to solve for N, right? So N, the number of moles would be equal to mass divided by molar mass. And so we can kind of do some substitutions to be able to calculate density. We also go over gas stoichiometry. Remember, stoichiometry problems really hinge on this idea that you can convert between the number of moles of any product or reactant in a chemical reaction based on their coefficients. And so rather than using molar mass and thinking about a mass to mass conversion, we can do any of our variables within the ideal gas law as what we're measuring, so like volume to volume or volume to mass, because we can use the ideal gas law to figure out the number of moles we have of a compound that's a gas, and then we can convert that into the moles we have of another reactant or product in the reaction. The other thing that we are going to cover, and this is kind of, I think of it within the context of kinetic molecular theory, is Graham's law of effusion. I think I spelled that wrong. And this is really looking at how particles actually behave, like their speed. And we'll see that their speed is going to be inversely proportional to their mass. So their velocity. And we'll look at root mean squared velocity. We'll throw out a lot of kind of big terms here. And I think it's easy to get lost in those. It's important to remember that it's not reasonable or helpful to look at the speed or the movement of just one gas particle, right? It's like just a little bit. And so we really want to look at the overall behavior. And so all of these different particles will have slightly different amounts of kinetic energy. And so we'll look at kind of like the average. We call it the root mean square average for how these gases are moving through space. And we'll see that in general, if something is smaller, it moves faster. And so we're going to equate this root mean square velocity for these particles with their molar mass. All right, that is our chapter in a nutshell. hopefully this is kind of some useful context as you dive into the details that are presented in the lecture. Good luck.